Okay, so we've seen that if we have 3 computers and 2 sciences, there's a bunch of ways to create strings with 5 words that have those exact counts. Each one of them has the same probability. Doesn't matter where science and computer show up, as long as there's 2 of them for science and 3 of them for computer. So each one of these strings is a different outcome, and they're totally disjoint. But they all have the same probability. So what I need to do is count, well, how many disjoint outcomes are there, and then multiply that by the probability of one of them to get the probability that any string had these counts. Okay, so to do that, I use something called the multinomial distribution. Okay, so let me first introduce just a little bit more notation. I'll say that let Pij be the probability that we pick word j out of our bag, given that we're using model I. So different models, or different classes, I'll say class I. Different classes have different probabilities of picking out particular words. Okay. I'll also let xj be the actual counts of word j in our dictionary. Okay. So let me now write down the multinomial distribution as a probability here. So I'll say that the probability that x1 is equal to a particular k, I'll call it k1, and x2 is equal to a different count, k2, and again we're assuming that we've got all these k's that they add to n, the total number of words in the string. So probability of all those, all the way up to the last word in the dictionary. How many of those did we actually see? So the probability of that, given that we're in class I, is equal to, okay, a couple things. So we've got this thing here, which you might recognize it. If you've seen the binomial theorem before, you might recognize some of this, but it's going to be n factorial over k1 factorial times k2 factorial times all the way up to kn factorial. Sorry, km factorial. Okay. So let's just look at that, what that looks like. So far we're not done, but oops, I need this to be here. Okay. So we have this factor here, n factorial over k factorial times k2 factorial up to km factorial. Okay. And also, okay, so this is actually the counts. This is how many ways you can move all these words to make a string, respecting the counts k1, k2 through km. But then what's the probability of each one? Well, it is going to be, well, p1 raised to, actually I'm in the ith class, so I'll say pi I1 raised to the k1 times pi2 raised to the k2 all the way up to p, so multiplying all these together, all the way up to multiplying by pim raised to the km. Okay. So that is the likelihood. But I also have, remember, I've got the likelihood for the posterior, I have the likelihood times the prior probability. So I also multiply this whole thing by the prior probability of class I. Let's say times probability of class I. Okay, so that's my whole expression for the probability. Now one thing that's kind of neat, or actually not the full probability, this is the posterior likelihood, right? Now one thing that's kind of neat is if we convert this into a log posterior likelihood, what we end up getting is, so this is a multiplication of 3 different things, which each shakes out in a sum. So let's say the log of p of x given ci. And actually, yeah, I really should change this to likelihood. Okay, so the log likelihood of x given ci is actually going to be the sum of the log of this part. Let's say log of that part, plus the log of this part, plus the log of the prior probability. Okay, so we were able to split this product up into this. And actually, what's really cool is you can split this up too, right? So this is a bunch of products here. So I can write this as the log likelihood is still log of this. I can't really separate this out in a nice way. I could, it's not worth it though. But plus k1 times the log of pi1. So plus k1 times the log of pi1 plus k2 times the log of pi2 all the way up to the log of pin times kn. So what's interesting is I've actually turned this into a linear equation. So it's yeah, so k1 log pi1. Okay. Anyway, so that's kind of neat. Now, another thing that you'll notice, okay, so this is getting very close to what we did in class, right? The thing that's different is that we have this extra weird factor in the front, which I never mentioned, right? But I did have you multiply a bunch of probabilities together. But I was also missing the prior probability. Okay. So I kind of had you do this part, but I never had you do this weird factor or this. So one thing you'll notice is that this is a constant, actually. For a particular observation x, this doesn't change. So we just have that number of words in the first. We just have that number of first words in the dictionary. We just have that number of second words in the dictionary. So this is fixed. So it's not going to change our answer if we add on a constant. So we can kind of ignore that. But then the other implicit assumption, though, that I wasn't as careful about was actually that this prior, if this was going to be a constant, then the classes would all have to have the same prior. So in other words, it would have to be equally likely in this 2016 debate example that Trump was speaking as Clinton was speaking. So there's an assumption behind what we did that I didn't state. But if you assume that they're all equally likely, and then you can just end up multiplying the probabilities together, or which in the log form turns into adding log probabilities together. So that's the model behind everything we're doing. So I'm just going to give you a quick sanity check on that to make sure it's clear.